It's good to be here. I'm going to talk about my work on revisiting qubit recycling. Basically, qubit recycling is a circuit optimization problem. It aims to reduce the circuit width, that is the number of qubits occurring in a quantum circuit. It is relevant because the number of qubits is one of the major limitations in current quantum devices. But qubit recycling is not reducing circuit width in an arbitrary way. It is restricted to these two circuit transformations. One is topological deformation. It means that we can slide the gate along the wires so that if two gates applied on disjoint qubits, they commute. Another is reusing discarded qubits. Here we use the triangles to denote the allocation and discard gates. And if we find one discard precedes the allocation, we can reuse the qubit as a fresh one by resetting it. And the operation on the right-hand side is actually the mid-circuit merriment and reset, which is recently available in practical quantum devices. So let's take a simple example to illustrate how we reduce the circuit width using these two transformations. So given the circuit actually first allocates 4 fresh qubits, do some computation, and discard 3 of them. So we first postpone the allocations and bring forward the discards so that the 2 of the discard gates actually precedes the allocations, and then we reuse them, and the circuit width is reduced by 2. And we may come back to this example later in this talk. So simply speaking, qubit recycling is to find a topologically identical circuit to reuse the maximum number of discarded qubits. This technique is not new. The earliest paper I can found is a paper appeared in 2016's PRA paper. They reported that they managed to reduce the circuit width by up to 90% using qubit recycling. And last year, there are 2 papers on this topic. One is CAQR, where they have reduced the qubit usage by up to 80% and with a slightly increased depth in circuit. Another work is from Quantinuum scientists, where they managed to reduce typical 80-qubit QAOA instances to about 20 qubits to run on their quantum machine. But there are still some questions not answered about qubit recycling. One is this complexity. The problem seems to be very hard because existing approaches on this topic usually uses heuristic-based algorithms, and the exact algorithms are of exponential time. Another question we can ask is about is there a better algorithm for this problem? And once we have a optimizer for qubit recycling, it is natural to ask how to achieve certified compilation. One approach is to through translation validation, but it might be infeasible or incomplete because checking equivalence of circuits is known to be QMA complete in general. And another approach is by compiler verification. Probably the best known work on this is Vox. But Vox correctness criterion requires the denotation of 2 circuits to be identical, which is overly strong for qubit recycling. We can take this example. On the left-hand side, there are 3 qubits, but on the right-hand side, the optimized circuit only have 2 qubits. And the resulting denotation of these 2 circuits have a mismatched dimension. Even if we trace out the discarded qubit, there's still a mismatch that the output qubits are actually not equal, but up to permutation. And lastly, managing matrices for permutation is painful. For example, if we want to permute 10 qubits, we have to have a unitary of more than 1,000 rows. So look at these questions. It seems like we lack a good abstraction for this problem to make use of the right existing results or techniques. And this will be the main theme of this work. So in the rest of this talk, I will first introduce our abstraction for the qubit recycling problem, which is a triangulation problem with respect to the qubit dependency graphs. And based on this abstraction, its complexity and heuristic-based algorithms follow easily. We managed to prove that the problem is NP-hard. And our heuristic is optimal for small circuits that we have evaluated. Finally, we managed to implement a certified compiler or optimizer based on this abstraction. And we make use of categorical semantics to organize and simplify our proof. So let's start with the abstraction. The first observation is that we can simplify the solution of this problem. To determine the solution of qubit recycling, it suffices to have a recycling strategy describing which qubit is reused by which other qubit. It can be formulated as an injective partial function between qubits, denoted by green hooked arrow. And q points to q prime means we can reuse the qubit q as q prime. To obtain an optimized circuit, we can simply add a green edge for the recycling strategy and do topological sorting on this quantum circuit, if you are familiar with the DAC representation. But not every recycling strategy is appropriate. An easily observed necessary condition is that the recycling edges should not introduce cycles in the circuit. That is, if we move from left to right along the circuit, for example, in this circuit, we can move from left along the red path and jump back through the green path. We should not return in the starting point, causing a cyclic dependency. And this is, in fact, also a sufficient condition for recycling strategy to be valid. So from the last slides, it is clear that what really matters in the circuit is whether there is a path from one qubit to another. So we can further abstract our circuit using a dependency graph. The vertices in the dependency graph are qubits, and an edge from q to q prime exists if either there is a path from allocation of q to discard of q prime, or q is an input qubit. That means there is no allocation of q, or q prime is an output qubit. That is, there is no discard of q prime. Intuitively, it means, for example, the discard q prime, if it's not appearing in the circuit, it means we will use q prime after the execution of the circuit. So it should have some dependency to the entire circuit. So we add this edge. And the previous constraint on the circuit becomes a constraint over the alternating path. That is, if we walk through the dependency graph along one black step and one green step, this path should be acyclic. And this and the QDG and the recycling strategy for the previous example is illustrated in this diagram, where we omitted self-loops. So we can see that our recycling strategy is from Q1 to Q2 and Q2 to Q3. And the alternating paths are not cyclic. And till now, we have shown that given a circuit C, to find a topological identical circuit C prime that minimizes its width is equivalent to finding a maximal valid recycling strategy with respect to C's QDG. And our last reduction step makes use of the adjacency matrix A of QDG. And the problem turns out to be equal to finding row and column permutations P and Q such that PAQ contains the maximal strictly triangular matrix B on the upper right corner. This is, well, a little bit complicated, but not surprising, because it is well known that if a digraph is acyclic, its adjacency matrix can be turned into a triangular one by permuting its vertices. But what is less obvious is that how to read out our recycling strategies from the permutations P and Q. I won't delve into details of how we achieve that, but to illustrate by an example, by our previous example. So we first label the columns and rows by the corresponding qubits. And then we do permutations of column and row permutations independently to put the zeros to the right upper corner. And once we obtain this green submatrix, which is strictly triangular, we read out the recycling strategy from its diagonal elements. For example, the elements with row index Q2 and column index Q1 corresponds to the recycling edge from Q1 to Q2. And that's how we recover the recycling strategy from the permutations. So putting these together, we obtain this diagram that to obtain an optimized circuit for qubit recycling problem, it suffices to find a recycling strategy which is valid and do topological sorting and qubit reusing. And finding the recycling strategy is actually polynomial time equivalent to a triangularization problem. That is finding independent row and column permutations. Based on this abstraction, the complexity and heuristic-based algorithms follows easily. We prove that the problem is NP-hard by reducing from Wilf's question. It asks whether, given a square matrix A, does there exist permutation matrices P and Q such that PAQ is triangular, which is very similar to our previous triangulation problem. And this problem is known to be NP-complete. So we managed to prove that we have a polynomial time reduction from Wilf's question to triangulation problem. So our qubit recycling problem is also NP-hard. So to solve this problem, we follow one row at a time manner. To triangularize the adjacency matrix one row at a time iteratively. So basically, we choose a row with zeros in it, the green row in the bottom, and swap it to the top. Then we do column permutations to put the zeros of this row to the right. And then we repeat the procedure repeat the procedure with the remaining submatrices corresponding to the zeros of the first row. And so what really matters is how we choose the next row in each iteration. Basically, there are two methods. One is to choose the row with maximum zeros in it, and another is to choose the row that maximizes the number of zeros in the remaining submatrix. So we also introduced the dual circuit technique by the continuum scientists. And it turned out that their technique is quite simple in our settings, which is triangularize iteratively column by column instead of row by row. Using these techniques, we have an algorithm that performs quite good. It achieves optimal for 76 out of 84 evaluated RevLib circuits. For the rest 8 of the circuits, we don't know whether they are optimal or not because they're too large to decide optimality. But our algorithm is better or is equal or better, although only in one circuit compared with the art. Okay, so the last piece of this work is about certified compiler for qubit recycling. It is also based on the previous abstraction, and what we really verified is the topological sorting and the qubit reusing module. So this is the workflow of our optimizer. Given an input circuit C, we first try to find a recycling strategy using the algorithm presented before. That is our solver in the gray box. And then we feed the recycling strategy to the sort module to do topological sorting. If the sort succeeds, it means the recycling strategy is valid, and we reuse the circuit and obtain an optimized circuit. Otherwise, it means our solver returned an invalid recycling strategy. So the sort module actually serves as a validator. It validates the recycling strategy and also rewrites the circuit C simultaneously. So here is where we kind of mixed validation and verification techniques. And we never have to verify the solver, so the proofs are actually robust to future updates to the solver. And what we really verified is that once the rewriter returns the result, the resulting circuit can be obtained by a series of the two circuit transformations mentioned earlier, which is a syntactic property. So the remaining proof obligation is to prove the soundness of these two circuit transformations. As we have explained before, we can expect an equality in their denotations, and we need better tools for manipulating permutations. So our solution is to adopt a symmetric monodic category as our semantic domain. And SMC, you may think of it as a well-organized and comprehensive library on top of matrices that isolates the elements that are directly relevant to our objectives. But SMC is not an arbitrary choice. It is actually a shared structure in commonly used semantic domains, such as superoperators and ZS calculus. So using SMC, we may find that the previously introduced key ingredients have a obvious semantics. For example, the topological deformation has its semantics as interchange law in SMC, and reusing qubits is actually applying isomorphisms, that is right and left unitars. And permutations becomes an isomorphism generated by associator and twists. And finally, the semantic equivalent can be defined by equality up to the above isomorphisms, and the soundness is straightforward. So in summary, we revisited qubit recycling by providing a new abstraction for it. And based on this abstraction, we prove its NP-hardness and provide slightly better algorithm, and implemented a certified optimizer making use of categorical semantics to simplify our proof. That's all.
Thank you. We have time for a quick question.
Thank you for a great talk. So in order to do qubit recycling, you need to prove that superposition, it is not, a qubit is not in a superposition, isn't it? So did you prove that?
I see. The discard gate, actually, you may interpret the discard gate as mirroring the circuit, mirroring a qubit and discarding the output. So after the mirrorment, it is actually disentangled from the rest of the system. Yeah.
I have a question about your heuristic. So you say the heuristic is doing very well. Could you say something about how fast it is compared to whatever methods people were using before?
I see. The time complexity is almost the same compared with the continuum team's work, but we evaluated their algorithm using our implementation. We did not have access to their implementation. But for CAQR, our method is much more faster than theirs, but they have many other considerations, such as they want to reach a balance between the width and depth, so it's reasonable to be slower. Yeah.
All right, let's thank our speaker again.
Thank you.